So in this lecture, we will see the time harmonic fields. A time harmonic field is the one where the fields vary with time in sinusoidal fashion. That is, they vary sinusoidally with time. So in general, field can vary with time in any pattern, but this is a specific case where the fields are varying in time in sinusoidal nature or sinusoidal function. So that is a specific case, and this is very important case. And in later lectures, we will deal only the time harmonic fields. So to understand the time harmonic field, we have to understand the phasor form first. So if you have a complex number z, you can represent this number in two, either in two form. One is you have the real or imaginary representation, or you can have in a magnitude or a phase form. So if you have a real line and imaginary line here, so if you have a complex number represented at this point, so you can identify this number either by using this real and imaginary component. You should know these two values to identify this complex number, or if you know the magnitude of this complex number and the phase, then you can also recognize the location of the z. So there are two forms, in the real or imaginary form, or is the polar form, or you can write z equals to r e to power j phi in the Euler form. So where x is real part of z, y is imaginary part of z, and r is the magnitude. If you know the x and y, you can compute the r, and you can have the phase tan inverse y over x. This is the phase of this complex number. Now here we have to revise few important properties, that if you multiply two complex number, which is the magnitude will be multiplied and the phase will be added. If you divide two numbers, z1 by z2, then the magnitude will be divided and phase will be subtracted. Now in another case, if you have a number a square z square or under root z, then how to proceed? It's simple, just have a revision. If you have some complex number whose representation, whose magnitude is r, and you have phases phi, or if you can write this as r e to the power j phi. Now if you have z square, then z square simply, if we square this term, then it will be r e to the power j phi whole square, and you will get the amplitude to be squared, and this will also multiply with this term, and it will be j 2 phi. So z square will have the magnitude r square, and the phase will be twice of the phase of the z. So this will give you z square will give you, give you magnitude to be r square, and phase will be twice of phi. Now if you have under root, if you have under root of z, then it can be written as r e to the power j phi half, and then it will be under root r and e to the power j phi by 2. It means under root z have the amplitude to be under root r and phase to be phi by 2, half of this. So this is very important result, and we will use later. So that if you take the under root of any complex number, you can just find the magnitude as the under root of the magnitude of z, and phase of this result as a half of the phase of the z. So here we will use this one. Now here we have taken the complex sinusoid because E is the complex sinusoid and where phi is some phase. Now we want to make this sinusoid varying with time because we have to deal with the time varying signals. So here it is constant. Now put up phi equals to omega t plus theta, where theta is a function of space only. It is independent to phi. So this making phi is equals to omega t function of time, then this complex sinusoid will become a time varying sinusoid. So therefore, putting phi equals to omega t plus theta will give you r e to the power j phi equals to r e to the power j omega t plus theta, and you can separate it out. It will become r e to the power j theta and e to the power j omega t. So this is a time factor, and this is a factor which is depending only on the space. It is independent to time, and we can write, if we have a real part of this, then the real part of r e to the power j phi will become r cos j phi, r cos phi, and phi is omega t plus theta, so you can have a r plus cos omega t. Similarly, immediate part of this will become r sin omega t plus theta. For example, let's take current it with a function of time. So instantaneous current is equals to I naught cos omega t plus theta. So we can write this as a real part of I naught e to the power j theta e j e to the power j omega t. That is, first you can write real part I naught e to the power j phi or omega t plus theta, and when you split you will get these results. Okay, so here this I naught e to the power j theta with the time factor e to the power j omega t can be written as is e to the power j omega t, because this is a function of space. This part is a function of space only, so we can represent as is, and this is called the phasor form. This is is called the phasor form of this function. So where is equals to I naught e to the power j theta, here it has a magnitude I naught and the phase is now theta. This phase is independent to the time. This is depending upon the space. Similarly, I naught depending upon the space only. So this IS is called the phasor form or the phasor current. Here is the current, so we can say the phasor current, but actually we will generally call the phasor form of this current IT. So if this is an instantaneous form, and we can represent this as a real part of is e to the power j omega t. So this is called the phasor form of this instantaneous form, and you can obtain the instantaneous form by using the phasor form using this equation. So this is important to know what is the phasor form. So phasor form is independent to the time. We can split the instantaneous form, that is the any vector or scalar which is depending upon the time, so we split in space and time, and then we can find its phasor form and we can do the further analysis. So this phasor form, this function is a, here we have the scalar quantity I. We can take a vector or a scalar. So in general, a phasor is a complex quantity and could be a scalar or a vector. Okay. So let if your vector A is a function of x, y, z, and t is in the time harmonic field. That is, this vector is varying in time in sinusoidal nature. So we can obtain its phasor form. So phasor form will become, if let this is an complex sinusoid. If it was a real, then we have to use the real of this. So let A is already a complex, so we can split into in spatial, that is the phasor form, and is the time form, time part. So you can write as A as x comma y comma z e to the power j omega t, or A equals to A as a. If it is a real, then we have to take the real part of this one, that is the real part of A as x y z over j omega t. We can represent any instantaneous value of the vector or scalar in terms of its phasor form. So Let's take, for example, if you have the complex sinusoid and you want to find out the phasor form of its derivative. We have this a, which is a function of space and time. When we want to obtain the derivative of this, and then we want to find its phasor form. So we can operate. So del a over del t will be del over del t of, we can represent in terms of its phasor form as e to of j omega t. This is the phasor form of a. Now you can take del by del t inside because this is independent to time. So you can take it out and you can differentiate this one. When you differentiate this function, you will get j omega as x y z. So here, when you differentiate, you will get the j omega term and this is the remaining term. So if you analyze this one, this is a whole quantity which is instantaneous some a vector here, and the what is the phasor form? If you split out the time part, the remaining part will be the phasor form. So the phasor form of this vector, which is new vector, is j omega as time xyz. The new phasor will be j omega times phasor. That is, you have del. For example, if you have a has a phasor form as, then del a over del t will have phasor form j omega as. This is how you can obtain. Okay. Now, if it is a real sinusoid, then you can have del over del t. If, for example, a is real, so we can del over del t. We can write in phasor form in this fashion: real part of a as e to the power j omega t. And again, we can take inside this del over del t, and then it is independent to the time. You can just differentiate what it will again have a j omega as. So this is again a real quantity. A is a real, so del over del t will be also be a become a here real. Then what we can have, the real part of j omega as e to the power j omega t. Now, if you separate it out the time, then this will become the phasor form of this one. So again, same concept. Either we can take the if it's complex, so again we are getting the same phasor. If it is real, then also we are getting the same phasor. So in both case, if A has the phasor form of AS, then derivative of A will have the j omega AS as a phasor form. Okay. Now same thing can be done for the integral. If you integrate, you can verify. If you integrate, then the phasor form will be, so the integration of A with respect to del t will give you the phasor form of as over j omega. Here it will be the phasor form. So this will be the, for example, here this is the phasor. You can separate out the time, it will be the phasor form. This is done for the complex vector. If it is a real vector, then you can have the real part of this here expression. So it means that we can write, if a signal, if a field is varying in time in sinusoidal nature, we can find out its phasor form. So if the fields are not varying sinusoidally or they are not time harmonic, there is no concept of phasor form. Phasor form exists only when you have the fields in the time harmonic nature. Now next is how to find the Maxwell's equation in phasor form. So we can directly find the phasor form. So let first equation is the del cross E, which is given by minus del over del t over B. So we can write it in phasor form. Let E equals to a real part of E as x y z is over j omega t. So it is a phasor form as ES, and we can write this instantaneous E as a phasor form of E in this fashion to be. Now when you have a curl of this E represent in the phasor form, and here B is represented in this form. So you can take inside the del operator, the curl of it will become curl of ES e to the j omega t. Now this is a function of spatial coordinate. So just taking the curl of this factor is same as taking the curl of ES because this is a constant with respect to the del. So your del cross Es will be e to power j omega t, and here it will become simply Bs is a function of space. So we can take del over del t over this part, and here again we have the j omega Bs. So for what we are getting, that real part of this one here we have, it means this is a phasor form. This part is a phasor form of this whole quantity, and here this is a phasor form of this whole quantity. It means these two are equal. So here from what we are getting, this is a term that del cross Es equals to minus j omega. So this is called the Maxwell's equation in phasor form. Now initially it was del cross E equals to minus del B over del T. In the phasor form, that del over del T is vanished, and now we have the j omega, because in the phasor form we have no concept of time, which is independent to time. So time will not come here. So we have reduced the actual Maxwell's equation in the phasor form in this fashion. Similarly, we can also obtain the phasor form of the other Maxwell's equation. You can go through the same process. So, for example, the second equation, this is the curl of H equals to the del D over del T plus J, and its phasor form is this one. So, actual was del, you have del cross H equals to del D over del T plus you have J. So these were it was a Maxwell equation, and you find phasor form, you will get del cross Hs equals to j omega ds plus Js. Similarly, you can go through for the another Maxwell's equation, that del dot D equals to rho Vs. So here again we have the real part of ds equal to j omega t, and similarly we have the rho Vs. So here, because there is no derivative of time, so j omega will not come here. So just you are getting a del dot ds equals to rho vs. Another, the last one is the del dot b equals to 0 will give you the del dot bs equals to 0 in the phasor form. So we can summarize these phasor forms in this table. So in the point form, it will become del dot ds equals to rho vs. These are all depending upon the space only. They are independent to the space. But they are all the phasor form of this one, actual D. D is actually different, and this is a phasor form. That is, we have splitted the time part from here. Simply that del dot bs equals to 0. Simply curl of es equals to minus j omega bs, and curl of hs equals to js plus j omega ds. So you have to remember that now del over del t, instead we have the j omega term here and here, and these are the integral form for the for the Maxwell equation in the phasor form. The next topic is a wave equation and their solution. Now to here onward we will start understanding the wave nature of the fields and how they look, what are their equations, and so on.